now is full screen. Can you see?
No, sir.
Okay, here you see?
Here I can see. Yes, sir.
Okay.
Can you change your slide so that I can confirm? Yeah, it's changing. You may proceed, sir. It's fine.
Okay. Yes, I have one issue on one slide. Okay. Okay. So good afternoon, everybody, and it's my real pleasure to be with you again. Thank you for staying with us. And today I'm going to talk about some work regarding the controlled radical polymerization of raw alkenes and give you some applications. There are many actors who has been involved in this work, and of course, Professor Sanjeev Banerjee, who came to my lab for 1 year and a half, has been very efficient, as well Dr. Marguer, who got a PhD thesis, and other people. So I come from Montpellier, which is located in the south of France, and next 10 kilometers from the sea, with a very nice city with a lot of students. Today, because we have to introduce the problem, is that if you consider polymers, they have different chain lengths. And because they have different chain length, and according to the way they are prepared, they can have a huge polydispersity or trying to find out narrow polydispersity. According to the application you are looking for, you need to control this dispersity. And for instance, if you are looking for mechanical properties, it's better to have a big, a wide polydispersity than a narrow one, because all the chain will act and will play their role. However, if you want to design some well-architectured polymers, it's better to have narrow dispersity, for instance, to be sure that all the chains in the second block, for instance, are initiated in the same way, as well as for graph copolymers. So this scheme represents the dispersity, and indeed, for conventional radical polymerization, you have a red dispersity. Can you see my pointer? Can you see the pointer?
Yes, sir.
Okay. So this is this red chromatogram is due to the non-controlled polymerization. On the other hand, the blue one is usually the signature of the chromatogram trace from radical control polymerization, called also RTRP. Okay. So the control of the polymerization is linked to very fast equilibrium between the dormant chain, which do not have any radical, for instance, and the active chain, which have radical. And the radicals are very reactive, very fugaz, and so they can react to many species in the medium, especially the monomers, but also they can trap some protons or from specific halogen in order to transfer. So you have to be very careful when you study a radical reaction, because we are talking about radical reaction, reactivator, deactivation, radical polymerization. So, and that these radicals are very, very efficient. And of course, they have a half-life also. They can be reactive onto specific groups also, specific sides of unsymmetrical monomers. And so you have to investigate all these different parameters to figure out if you are able to make a very good control. So this fast equilibrium is very important, because when it's possible to make the cleavage in order to allow the formation of macroradical, the macroradical can react on the monomer, which is what we expect, in order to make an additional chain extension, and then come back by the presence of, for instance, a chain transfer agent or metallic salt or anything. So you can have. So this also is very interesting because you can have a possible reactivation. So this means that if you make a first polymer with a specific group, this polymer can act as initiator or chain transfer agent in order to promote the synthesis of a block copolymer. I mentioned in my first lecture that the evidence of a controlled polymerization is the linear increase of the molar mass or average degree of polymerization versus the monomer conversion. This is very important. Many reports state that the linear evolution of consumption of monomer versus time, or narrow dispersity versus time, or anyway versus time, this is not good because it's a kinetic first order reaction. This is not linked to the control of the polymerization. So keep in mind, if you're looking in this area, you have to evidence the linear dependence of the molar mass versus the monomer conversion. So of course, block copolymers can be prepared. So the question is, may we anticipate the synthesis of high value added material like fluoropolymers? It's a major question we have to ask because, as you know, the fluorinated monomers are specific reactant. These are gas also, so you have to handle the reaction under specific groups. And oh, I have a problem with one slide. Okay, so it doesn't appear. I don't know why. I have one slide which shows the different techniques of polymerization. As you know, there is NMP, okay, on the left, based on the dissociation combination. So, for instance, Otsu in the early 80s developed the concept of photo-initiators. Initiators means initiators, transfer, okay, and they could be used. This system could be used as a specific system in order to release the radicals and to be also to undergo the transfer by this dithiocarbamate. Another strategy is the nitroxide mediated polymerization. So the most well-known is TEMPO. This is SG1. SG1 because the first person who developed this was Sandra S. Grimaldi, GSG. And as you can see, this cannot initiate the polymerization, but reacts with any radical in order to lead to this dead chain, which can go this equilibrium to lead back to the monomer. This is applied to styrene, acrylate, methacrylate, etc. The second family is based on atom or group transfer. So you know that Chris Maciejewski in US or Dave Hamilton in Warwick or Mitsuo Sawamoto in Japan used a lot of metals, whatever the copper, or some ruthenium for Sawamoto. And the idea was to have a specific group which undergoes, a specific metal undergoes an oxidation, a degree of oxidation higher than this, concomitant to the formation of a radical. And indeed, there were these copper or ruthenium complex were complexed by ligand, just like bipyridine, this imine, or this tren, this tetra or pentamethyl tetramine. Okay. And then there is another family which is based on the degenerative chain transfer. This means that you add in your system a chain transfer agent, which is able to allow the control of the polymerization. And indeed, you have two main systems, iodine transfer polymerization based on iodine. Usually this is well adapted to fluorinated monomers because the resulting CF2I has a very low bond dissociation energy, which enables to lead back to a radical allowing the reaction with the monomer for extension, for growing a radical. And then the transfer is very efficient so that the radical here formed can be transferred by the RFI to lead back to the iodine. Another possibility is RAFT, reversible addition fragmentation chain transfer, or MADIX. MADIX is macromolecular design as the interchange of xanthate. So this is a dithioester, but you can use the xanthate, you can use trithiocarbonate. And in this case, the same strategy is that the polymeric chain generated during the initiation, okay, is going to react onto usually the sulfur and then change, rearrange, fragment it in order to make a new macro initiator or new micro dithioester or xanthate or trithiocarbonate, etc. So this is very important because in this case you can do a lot of things. And my first point is iodine transfer polymerization. This was discovered by Tatemoto in the late 70s, you know, and unfortunately Tatemoto didn't tell about the contra-radical polymerization, though he could evidence the linear dependence of molar mass versus the monomer conversion. But later, Maciejewski in the mid-90s, so let's say about 20 years later, suggested the concept of contra-radical polymerization, but indeed, Tatemoto was the first pioneer who discovered this typical reaction. So as you can see, you have the initiating radical is going to react onto the monomer, then you have a propagation and leading to the chain transfer in which this iodine containing radical is going to be transferred by the iodine here to make a kind of telechemical compound, leading back to a radical able to react onto monomers and to propagate in the system. So this was very interesting because this concept already illustrated a lot of ideas. And in Daikin Company, because Tatemoto was working for Daikin Company, they used this concept in order to prepare thermoplastic elastomers. A thermoplastic elastomers is a kind of segmented polymer in which you have amorphous state and thermoplastic state, just like more or less a polymer in which you have a crystalline and amorphous state. But the strategy was very smart, because starting from a diiodo compound, which fluorinated, for instance, IC6F12I, with a monomer B, which was chosen so that it could give some soft segment, for instance, VDF-HFP 7525. If you take VDF-HFP 9010, this is crystalline. But in a higher content of HFP, the site CF3 is going to break the crystallinity of the PVDF, allowing some amorphous. Okay, so this is the same for VDF-CTFE or VDF-HFP-TFE, etc., etc. So this is AFLAS, which is an alternating copolymer of TFE and propylene, but the TG is rather high, -1. While for other systems, the TG is rather low. It can reach as low as -33. So the formation of this soft segment diiodo compound could be used as a new chain transfer agent in a further polymerization of monomer A. For instance, VDF, ETFE, or ETFE-PMVE, performative vinyl ether, in which you have different content to have some crystallinity, and the crystallinity could range between 160 for PVDF to 267 for ETFE, or even 327 for PTFE. So this SEM sketch represents the different crystalline zone and amorphous zone, and indeed the Daikin Company, which produces the diel, these are these thermoplastic elastomers in a two-step, they can be cross-linked by the crystalline zone, okay, by specific interaction. So Vuitton products from DuPont or Technophrom from Solvay Solexis were developed later, of course, in a different strategy as reported or claimed in the patents of daikin. We tried to investigate this reaction a little bit deeper, and we used in a lab, it was more than about 20 years ago, we used different chain transfer agents. One was C6F13I, the second one was C6F13 VDFI, and then it was also the isomer of VDF, as you can see here, the CF2I, and now this chain transfer agent has a CH2I. It was very interesting to compare the efficiency of both chain transfer agents because, as you know, I mentioned that last Friday, the bond dissociation energy, which is necessary to allow this fast equilibrium between the dormant chain and the living chain, this BDE is very important and is going to be the driving force of a reaction. So we did 3 reactions. We monitor the reaction by sampling, and we measure, of course, by NMR, by GPC, by TGA. We measure all the different characteristics, and we compare all of them of the resulting polymers. What you can see for the first 2 cases, we had some growing chain. Okay, so we have a nice regular increase of molecular weight. Okay, with a narrowing of a polydispersity. And this was already a kind of good feature to expect a possible trend of control. However, in the last example, where you have a CH2I, you can see that you don't have an increase, a regular increase, and the polydispersity is more or less the same. So showing that the use of this chain transfer agent is not so obvious to control the polymerization. So what I mentioned is either by molar mass or by degree of polymerization versus the VDF conversion. So this was the first, in the 2 first case where we have this kind of evolution of molecular weight. You can see up to 70%. Okay, this is 50%, 30%. So we have a much higher molecular weight and a kind of narrowing of the dispersity. With a control, okay, I told you this is the evidence of a controlled polymerization, while on the third case, sorry, you have an increase and then a decrease showing that this chain transfer agent has a kind of chain transfer agent in telomerization rather than in controlled radical polymerization. Interestingly, the Malditov was very nice and very narrow also. We have a nice dispersity by Maldi, showing that this is in the 2 first case, showing that we had this tendency of controlled polymerization. Now, I would like to give you an example regarding the feature, the use of the controlled radical polymerization. And unfortunately, I have to mention a dramatic accident in January 1986, where the Challenger shuttle exploded 75 seconds after launching. And in front of the commission, the jury, which give a testimony of this accident, has to give proof. And this is Professor Richard Feynman, who is a Nobel Prize in physics. He took the O-rings, the packing of a shuttle, and dropped in ice water. Immediately, this gasket broke because the glass transition temperature of this material were not were very brittle at low temperature. So the thing is, since this accident, indeed, all the gaskets are made of fluoroelastomers, and indeed, the feature is to find out the low TG. And if you look at copolymers, just VDF, HFP, and TFE, the TG is not low enough because the -26 is not low enough. And pentafluoropropylene VDF, which was a competitor of HFP, was not even better. Even perfluoromethyl vinyl ether with TFE, TG was not lower than -15. Even with ethylene TFE, not better. However, the presence of VDF and perfluoromethyl vinyl ether was very interesting. And even if you have hexafluoropropylene oxide, you have even much lower thermal stability, TG. So the idea was to prepare some copolymers containing VDF and PMV by iodine transfer polymerization. And this is an action we developed in collaboration with DuPont, indeed. If you look, there is another requirement, is the heat resistance versus the oil resistance. And of course, the requested products are in the top right. And fluorinated elastomers are very good, knowing that for fluorosilicons, there is a backbiting reaction. When you heat it up, you create some cycle which is not very good. So the best idea was to use VDF and perfluoromethyl vinyl ethers. This chart represents the different fluorinated olefins, the most commonly used in polymerization. And as you can see, the boiling points, these are all gases, okay? So we perform some iodine transfer copolymerization of VDF and PMV in autoclave. This is an autoclave with a controller, with a manometer, with a steering system inside. This is the heating mantle. We did some radical polymerization under sodium persulfate with diiodo compound in order to prepare diiodo compound containing VDF, PMV, and what was very interesting, the C4F8 center was a very nice label in fluorine NMR to figure out the number of VDF and the number of PMV. As we know, PMV does not homopolymerize, but we saw that it was possible to copolymerize, okay, and this was monitored by Malditov. For instance, for 1 unit of PMV, you have a red distribution. For 2 units, we have a blue distribution. For 3 units of PMV, you have a green distribution. For 4 units, you have this orange distribution. And for 5 units, it was possible. This is a model reaction, of course. And we saw that according to the evolution of time, we have narrowing the dispersity, increasing the molecular weight, and we show that we have a good control of the polymerization by the linear dependence of molar mass versus VDF conversion, though we had a slight increase of the degree of the dispersity, which is linked to the CH2I, which is obviously generated during polymerization. And we'll come back to that later. So, and of course, by TGA under air, we have a satisfactory stability. And as you can see, the higher the molecular weight, the better the thermostability.
Sir,
so why did we... Pardon?
I have a query in the previous slide where you showed the Malditov.
Is it possible to do that at the end? Because I have 1 hour.
Sure.
Okay,
sure.
Thank you. Okay, so the idea to make a diiodo compound containing VDF and PMVE was to change this iodo into functional group in order to promote some cross-linking. Because the idea of DuPont in this project was to have some cross-linkable copolymers which were used for aerospace, especially for these gaskets. And what was important is to make the cross-linking and to keep low TG. The low TG, we reach about -40, -50 in these conditions. So we decided to chemically modify the diiodo compound into diacrylate via 2 strategies, ethylation, then oxidation, then acrylation. And you have here a C2 spacer between the polymeric chain and the acrylate, or addition of 2 allyl alcohol, reduction of a iodo compound, acrylation in order to have a C3. And this strategy was much better, with better yield than this one, because this reaction was a bottleneck in this way. So the way is, from this kind of liquid, it was possible to make a cross-link network in which we have a very soft system of about, TG was about -45, which was very good because, as I showed before, except the copolymers containing perfluoropolyethers, we didn't have any so low TG. So we had also different, okay, we have different projects on that, but I have to change to another possibility is the work developed by Azande in order to make some iodine transfer polymerization in the presence of manganese CO 10 times. And this catalyst enabled to trap the iodine to make some radical and to favor the formation of PVDF-I and even to go to the diblock copolymers with styrene, butadiene, vinyl chloride, vinyl acetate, methyl acrylate, acryl nitrate. So this researcher at the University of Connecticut did some photo-mediated iodine transfer polymerization in visible. You can see here one is experiment. You see with different system here, different colors, and he could evidence the linear dependence of molecule weight versus conversion and the, let's say, the narrow dispersity. Let's say narrow dispersity 1.48 is still a little bit high because there are some reverse addition. I will go back a little bit later on that. So also we did from this work in partnership with Professor Banerjee, Sanjeev, we did some nice work in order to use some radical initiator which has the same structure of a chain transfer agent. And this was the idea because at the end we knew that we have a CF3 end group. So we could make some CF3 PVDF or diodo compound containing PVDF on which you can see the nice, with a refractive index, of course, detector, you have a negative value because PVDF has a very low refractive index. And you can see here the nice linear dependence of molar mass versus conversion and also the low dispersity. So we have a first order kinetics by the evolution of monomer and conversion versus time. Also, in a similar project, we had a collaboration with Honeywell, and it was necessary to make block copolymers by containing a high amount of CTFE and even some chlorine. Chlorine enables to make better coatings. And indeed, when you copolymerize CTFE and VDC, you have a very high reactivity of VDC, so it was necessary to combine a compromise, to have a compromise with a high content of CTFE and a suitable amount of VDC to allow some characteristics, as well making some block copolymers with starting either from PVDF or from this copolymer. And as you can see here, we have an evolution of the GPC traces versus the reactions. What happens is this iodine transfer polymerization is very interesting, but there are other technologies, and especially RAFT, MADIX, and other systems I would like to mention now regarding HRP or NMP. And as you know, RAFT polymerization, which have been well described by Rizardo and Moad in Australia, ICIRO, as well as Brent Summerling, macromolecular, and Sébastien Perrier on Warwick, nice papers. There are still a lot of work which is based on this reaction. So the presence of this, I speak about xanthate, okay, in this case. So usually the initiator leads radicals. The radicals initiate the polymerization of N monomer, making a polymer radical. The polymer radical reacts onto the sulfur to make this intermediate, then rearrange to make a polymeric xanthate. And then this polymeric xanthate can change again, and you can have even chain extension to make some block copolymers.
This session will end by 6:50.
We have been working rather carefully with different xanthate or dithiocarbonate to make some linear chain, some block copolymers, some graft copolymers, and some star. And I will be happy to show that to you now. So the first reaction was a model reaction in which we used VDF and this kind of xanthate in the presence of this trigonox 1:1, which gave a cleavage between oxygen extrusion, and then this initiate the polymerization and then the control. This chain transfer reaction constant is so high that is going to react almost over all the radical present. And we did the reaction into dimethyl carbonate, which enables to solubilize these polymers. Indeed, if you look at VDF, usually you consider that it's a non-symmetrical monomer which has a head, CF2, and a tail. So in the case of polymerization, you have the propagation, which can be head to tail, okay? And with the CTA, of course, you have this macro PVDF terminated by CF2 xanthate. But the problem is also it's possible to have what is called the head-to-head. And in this case, the radical generated is terminated by CH2, which reacts onto the xanthate in order to make this macro xanthate in which you have a CH2 xanthate. So you can see that you have two different possibilities, and indeed you can anticipate, because of the electroweaving effect of fluorine, the bond dissociation energy of CF2S will be weaker than that of CH2 xanthate. And in this case, you can see that here you will have a fast equilibrium releasing radicals reacting onto VDF, but here you can have not the same efficiency, and in this case you can have a poor reactivity with VDF. So this is important to consider, and anyway, this was the PhD of Mark Gere, who did this reaction, showing that we have a nice control by the figure of the GPC. Indeed, during the reaction, we could see that there is a kind of latence, and then you have a linear control, and then it goes very fast, showing that there is something which happens here. And if you look at this is versus time, monomer versus time, when you look at the evolution of monomass versus the conversion, you have a linear dependence. And you see here that you have an increase of the dispersity. Of course, we are less than 1.4, but the presence of this increase indeed, which is reluctant to a real control, is because, as I mentioned before, there is this head-to-head addition which gives the CH2 xanthate. However, the MALDI was very nice. And as you can see, we have a very nice separation of 64, which represent VDF units between the different signals. And it was also possible to see by my spectrometry the different adducts. And we had, in a positive mode, we have this nice distribution in which we could see the both end groups of the xanthate out of the PVDF chain. You can understand that we don't go high in molecular weight. You know, 3,000 means we have 50 units of VDF. So it's not a polymer, it's rather an oligomer. The NMR was very good also. It's a pity there is no animation because we could see the good assignments. But let's say this is VDF reverse addition, the tail to tail. This is reverse normal addition, head to tail. And then you have the different units, VN groups, coming from the xanthate here and here. And here you have the ethyl group coming from this big xanthate here. So methyl, sorry, this methyl is here, this methyl is here, and this CH3 here is here. So we can see all of them for a reasonable, maybe it's 20 or 25 molecular weight or VDF, we have a high intensity. But still, what is very interesting is that the content of tail-to-tail is very small compared to that of head-to-tail. Usually you have 8 to 10%, but here it's even lower. By fluorine NMR, also we have very nice system. So if you are not familiar with fluorine NMR, it's like proton NMR, but we did a 2D NMR, and we could see really the presence of a CF2 in which we had some correlation. We have also the presence of the reverse unit here, and then we could see also of course, the nice head-to-tail addition from the fluorine NMR and from the proton NMR, and also we see some little bit transfer linked to the CF2H in the system. However, by doing some kinetics, we could see that after 5 hours, we monitor the reaction by the presence of the CH2 and the CF2 here, and here. And as we can see, there is an increase of the presence of the CH2S, versus the reaction. So this is a CH2F, and you have a decrease of the CF2S, which was evidenced also by fluorine NMR also. Okay. And as you can see here, this was shown in this scheme regarding the chain end functionality, which is decreasing versus the conversion, as soon as the total functionality was not 100%, but let's say we go to 90% for functionality, because we have this problem with CH2. But the question was, is it possible to go to higher molecular weight? And the answer is yes, it was possible, but we were limited. If you target 100 DPN, we had a value of about 60, 70 in functionality, and still we observe that we have this evolution, this increasing evolution of the CH2 xanthate due to, unfortunately, the too strong bond dissociation energy. And of course, as you can see here, the black curve show that we have a fast consumption of the CF2 xanthate in the system. And also some a little bit transfer from the DMC, because DMC has OCH3, in which CH3 gives some transfer. So as you can expect here. And even the DMC participate in reacting with xanthate, and in this case it was another bottleneck. But in principle it works. We have been very deep in this reaction, so we published a couple of papers, and even we wanted to go a little bit further in order to see if it was possible to make some architectures based on VDF. So I'm really sorry, because the animation should show all the different strategies of making some star, some nanoparticles, some block copolymers, graft copolymers, and dendrimers. Unfortunately, you cannot see them, but I will try to give you some examples in the following slides. So the first one was, is it possible to make block copolymers? So the first action is when you start from this macro xanthate, you put some initiator and as AIBN and a monomer. The monomer can be N-vinyl pyridone, acrylamide, or vinyl acetate. We could see that by controlling both the GPC and the fluorine NMR, we show some differences. And indeed, when you do some, the black curve is assigned to the PVDF xanthate. Okay, so we go to high molecular weight to the right, and as you can see with the red, it's an N-vinyl pyridone. We have a very broad dispersity, and indeed, what you can see is you don't have an evolution of this N group, because what is important is the presence of this N group is the CF2, which is adjacent in beta position of the xanthate. And indeed, here we don't have any evolution. The same tendency was shown on the blue one with acrylamide. And it's very broad, even you have a kind of binomal distribution. And you can see with the blue one that you don't have the same, you have the same ICE, and it doesn't make any sense that the reaction occurred. However, with vinyl acetate, which is very good controlled by xanthate, first, you can see that the GPC has a very narrow trace. It's less than 1.4 for a diblock copolymer, so which is rather exceptional in this case. And when you look at the fluorine NMR, the little signals on the left here disappeared, showing that you have a good presence of the second block assigned to the VDF. So showing that the CH2 sulfur or CF2 sulfur disappeared by the presence of vinyl acetate. So this was very interesting, and even we wanted to go a little bit further to make the hydrolysis, because in case the polyvinyl acetate is hydrophobic, however, if you are able to hydrolyze into vinyl alcohol, this gives some hydrophilic sequence, And this was well identified by NMR. When you look at the PVD, polyvinyl acetate moiety, after hydrolysis, you lose the characteristic CH3 of the acetate. And even by IR, this is the PVDF, this is the PVDF acetate, and after reaction, polyvinyl alcohol shows that you have a presence of OH and the disappearance of the vanishing of the carbonyl of vinyl acetate. So in this case, it was very interesting to evidence by both techniques we had hydrolyzed the vinyl acetate into vinyl alcohol. So after dialysis for purification, it was possible by light scattering to see that we have a kind of monodispersed particles. And in water, we have some micelles in which the core was made of freenated compound, and the shell was a kind of core shell was made of some polyvinyl alcohol compound. This was very nice pictures from Professor Ishit Almond in Israel. And then Mark went to Professor Kabigaito, because Kabigaito-san did a lot of work in cationic polymerization of xanthate. And we say, why not to use his polymers terminated by xanthate to make a chain extension with VDF. And in addition to the xanthate, he used this diphthiocarbamate, this whatever aliphatic or aromatic, and it was possible also to use this. So Mark did a lot of work on cationic polymerization of vanilla ethers, and then he showed that he could reach very narrow dispersity in this case, because it's cationic less than 1.1, okay, in all of them, maybe here, and for us you can see the difference. And so showing that the xanthate was working with vinyl ethers in cationic polymerization, and then he did some specific reaction involving this polyvinyl ether xanthate or diphthiocarbamate in order to make a chain extension with VDF, and indeed this works. As you can see, we have a shift of a signal of NMR, whatever you have aliphatic or aromatic diphthiocarbamate or even this xanthate. With polydispersity in this case, which is high, 1.50, of course, but this preserves very narrow dispersity in this case, showing that at up to 30–40% we have a linear dependence. So this was possible to make also some this slide is much better than the previous one, 4-arm PVDF. How to make it? It's possible to do with, of course, xanthate, a tetraxanthate, as showing a 4-arm. So polymerization of VDF with tetraxanthate led to a 4-arm PVDF. And in this case, with the presence of hexylamine and triethylamine, it was possible to make some Michael-Fayol reaction onto the less hindered CF2 to make this tetra metacrylate, which could be polymerized in the presence of photoinitiator. With, as you can see, there is no light, and we have this whitish product. And after UV polymerization, it was possible to make a film on which we measure some water contact angle. So we put a drop of water onto the coating, and we noted that in certain case we have some hydrophobicity. I just remind you that the hydrophobicity is higher than 90 degrees, and this was in the case we use some metacrylate containing perfluoropolyethers. So even it was lipophobic, oilophobic, hydrophobic, okay, in the presence of that, and the surface tension was 8 millinewton per centimeter. So this strategy was also applied for lithium-ion batteries, and we collaborate with Professor Patrikos in Cyprus, and also with Professor Jean-François Goury at University Louvain in in Belgium. So you need collaboration with many groups if you want to go further and if people want to use your samples. So the same strategy was used in order to make some tetra alcohol. You see that we have a very nice shape on SEC. And this tetra alcohol was reacting with this dibenzoic acid in order to make some specific group containing polyvinyl alcohol, PEG. So we had a co-network based on PVDF with 4 arms and PEG 4 arms to make this kind of specific groups for lithium-ion batteries, especially when lithium perchlorate or LiTFSC were used. So these are the action of Jean-François Gouy, who is an expert in ionic conductivity and electrochemistry. And what you can see that the evolution of the ionic conductivity, especially the lithium cation conductivity versus the temperature. So you see the temperature here. So this is in Kelvin. So we go about to 80 degrees. We can see that we have conductivity ranging between 0.5 and 4 millisiemens per centimeter. When you have 1 millisiemens per centimeter, it's already a good result. So we have 4, which we were very satisfied with this result. So another application was developed by Professor Katsialous in Netherlands. So Katsialous did some dead-end polymerization of this peroxycarbonate, this perester, making some homopolymerization of EDF, terminated by compounds which can be functional, on which they can have some OH group by polycondensation or by acido group after making some acidation or triple bond. And here, the second group was by control radical polymerization of styrene or vinyl pyridine in the presence of tritiocarbonate to make this kind of product for which she prepared some tri-block copolymers. I'm sorry, this goes a little bit fast. I gave a presentation 1 hour ago, and I did already these comments that the group in Groningen, in this Katsialous, was able to change and to put different function in order to allow either clean chemistry or condensation or to make some tri-block copolymer. So the central block was PVDF, and then the external block were either polystyrene, polyethermethyl acrylate, polynipam, or so they monitor the reaction by SEC, and also they measure the electroactive and especially the displacement electrical signal regarding the behavior if they have some ferroelectric or piezoelectric tendency. Okay, before I finish, I would like also to underline some nice work developed by Eiver Atsushi Goto, what is called the radical chain transfer catalyzed polymerization with specific catalyst. It can be iodine also, or the CMRP, cobalt mediated radical polymerization, developed by Antoine de Bouin and Christophe de Trembleur in Liège, in Belgium, and also by Professor Yamago regarding the use of tellurium, antimony, and bismuth. And indeed, Professor Banerjee went to visit Professor de Bouin and de Trembleur at the beginning of his stay in order to see if it was possible to prepare some sample in order to, especially containing cobalt-free or cobalt-2 ACAC, in order to make some polymerization. So he did some reaction. He did first some preparation in Liège and then used this product in Montpellier. And what happens is he was very successful in making this control radical polymerization. Okay, so so by OMRP, a nice work was done, and this was the work of Sanjib using this very interesting oligo vinyl acetate terminated by cobalt-free ACAC. It could undergo the polymerization of EDF, but you have to quench the unstable cobalt ACAC, especially to air, with a tempo which is stable in this case, so that he could analyzed by GPC the presence of the PVDF tempo, and then after diblock copolymers with vinyl acetate, it was possible to make a chain extension and to have nice products. So the work was supported by French National Agency, and again, we could monitor the evolution of Mn versus conversion and to see that this polyspercity index was very low. So in conclusion, I have 5 minutes more. Is okay?
Yes, sir.
Okay. So what can I say in conclusion is just to mention that there are still many strategies to prepare some well-designed fluoropolymers by ITP. This is traditionally done by at Daikin, but also raft polymerization seems to give very nice evidence of these results, and also by cobalt mediated radical polymerization. So the evolution of the situation was in 2010. There were some action regarding the application on dielectric material anti-fluid membrane. Now it's more and more for battery, lithium-ion batteries. And indeed, you see that you need the expertise of chemists and physicists also when I think about electroactive polymers, and also from people involved in energy, lithium-ion batteries, fuel cell membrane, proton conducting membrane, etc. So it's very important. Something I've not mentioned is the photoraft polymerization. So growing interest on photoraft since a couple of years regarding the use of photoinitiator to release the radical, and then the raft has been applied, and Cyril Boyer in Australia has done a lot of work on that, nice reviews. The same strategy, indeed, Professor Zandey didn't do raft, but ITP on the visible. And what happens is the work of Professor Chen regarding the controradical copolymerization of TFE or CTFE with vinyl ethers was possible to make alternating copolymers in the presence of xanthate, for instance, but you have this sometimes with this dimethyl carbonate, you have some DMC, you have some problems with transfer. The work on raft polymerization, photopolymerization was well developed by Professor Chen in Fudan University in China, where again he had to carry out the reaction in ampoules with visible light, green light, and so he could evidence the control of the polymerization by the different use of different chain transfer agent, whatever he used, some xanthate or trichalcobronate, etc. This one and this one. And even the what is interesting, the presence of this 2CF3 enabled to monitor reaction by fluid NMR. And as you can see here, in different, they could achieve very interesting reactions with different monomers, fluorinated monomers, perfluoromethyl vinyl ether, this kind of dioxolane, this PPVE, or this is the monomer from NAFE, more or less without any sulfonic fluoride, but they could do a lot of different combination of these electro-withdrawing monomers, fluorinated, and electro-donating monomers, vinyl acetate, NVP, and this vinyl ether, and they can see that with off, no reaction, on, UV on reaction, off, no reaction, on reaction, off reaction, etc., etc. So this is a very nice work, which is difficult, of course, to apply to industry because you carry out the reaction in small ampoules, and of course the pressure is not so high. So we did also some work on the photopolymerization of EDF with xanthate, and it worked well. Kimi Zhang did the work in a lab, but always the same issue was the presence of CH2S adjacent to xanthate in these conditions. So in conclusion, I hope that I convinced you that it's possible to do some contraradical copolymerization of fluoroalkenes especially by ITP, RAFT Madix, or cobalt radical mediated polymerization. I didn't insist on that, but of course the structure of a comonomer is very important for the property and the application of the material. So it's possible to design some nice architectures, block, graft, gradient, alternating copolymers, so hyperrange, dendrimers also. I didn't speak about dendrimers, but there are some work, and we did some work in the lab also. And of course, the applications. Think about the applications because it can be very interesting to attract industry. You have a lot of industry in India, and so they can be very interested to co-work with you. And think about, of course, the nowadays application are energy with also fuel cell membrane, lithium-ion batteries, of course, alternatives to PFOA and PFOS, perfluorooctanoic acid, perfluorooctane sulfonic acid. I will speak about that tomorrow. Lithium-ion batteries. I didn't speak about PISA, but we did some PISA in the lab about smart additives, etc. And before finishing, I would like to thank all the people involved in this project. Of course, I didn't do all of them. I just supervise and manage with my knowledge. Of course, Professor Sanjeev Banerjee, Marc Guerre. We have a lot of collaboration with Professor Kamigaito in Japan, De Bouin in Liège, Renando Poli in Toulouse, Kostas Patrikos in Cyprus, Jean-François Gouet in Belgium. So, and Ishit Almond for NICE, SEM, and Judy Smith. So, and of course, Arkema supplies the VDF, Tozo supplies some trifluoroacrylate. We have some support also from GSPS, from French National Agency. And I would like to thank you very much for your kind attention. Thank you.
Okay, so thank you, Dr. Ameduri, for your nice lectures. So today's session is over here. So we'll be back tomorrow 3:30 p.m. IST with Dr. Ameduri's remaining lectures.
Okay,
thank you to the participants for attending. Yeah.
Sanjeev, I
kept
minutes for questions.
Yes, please. Yeah, please go ahead.
Sir, you mentioned about the multitude of fragments. So does the junction point breaks and give the fragment, or is it the side chains which break down?
It's a good question. I think that in the ionization effect, you have a lot of things which has been destroyed. And the idea of MALDI is to rebuild more or less the molecule. Because when I show different MALDI spectra, and indeed what happens is if you work on negative mode, you will see a lot of fragmentation. But in positive mode, we have a much better figure, much better data in order to rebuild the molecule. For instance, VDF is stable, and we could see all the fragments separated by 64, which is the molecular weight of VDF. So in this case, if you do some MALDI in your investigation, please consider the positive mode and not the negative mode.
Okay, thank you so much.
Is it clear?
Yes, sir. Thank you.
You're welcome.
I think as we don't have any further queries, we thank Dr. Bruno for this wonderful session and will join tomorrow for the further sessions. Thank you, sir.
Okay, thank you very much. Goodbye. See you tomorrow.
Goodbye, sir. Have a nice day.
Bye-bye. Thank you.